Okay, good afternoon or morning or evening, depending on where you are. Everybody, thank you for joining this online seminar series from the hosted by the Department of English and Communication at Hong Kong Polytechnic University. And today, it's our pleasure to have Dr. Andrea Nini, who is Associate Professor, so Senior Lecturer, but equivalent of the Hong Kong ranking here in linguistics and English language at the University of Manchester in the UK, where he teaches courses in forensic linguistics, statistics, statistical analysis for linguistics. And he is known for his work in the field of forensic linguistics, specializing in authorship analysis and forensic text comparison using computational approaches. So he's also carried out research and published in other areas in linguistics, such as computational sociolinguistics, register variation. And apart from his academic work, he also offers consultancy as a forensic linguist to law enforcement agency, predominantly in criminal cases involving documents of disputed authorship. So the topic of his talk today is interpretable cognitive linguistic authorship analysis using likelihood ratio framework. So without further ado, I should pass the mic to Andrew. Imagine there's a mic here. There you go.
Thank you, Bruce. Yeah, thank you for inviting me. It's a pleasure to be here, although of course virtually. Um, it's a very long title, I realize. Um, and um, and that's because there is a lot that I cover in this talk. So the main topic of this talk is authorship analysis. But the point I'm going to make is that we can do authorship analysis in a way that is more linguistically plausible than scientifically plausible, and as well as meeting the requirements for best practice in forensic science, which is to adopt the likelihood ratio framework. And so I'll talk about a new method that colleagues and I developed that we believe meets this desiderata for a method for authorship analysis. But I'm not sure about the audience, so I'm going to just give a sort of introductory notes about a little bit of everything I will talk about, including authorship analysis. So let me just begin with that. So what do we mean by authorship analysis? Um, let's say we have a disputed document and we don't know who wrote this document. If we have if we have a close set of candidates who could have written this document and we have data that we can use for comparison, then I mean, typically the literature in computer science mostly calls this problem authorship attribution problem. So where the problem is to identify who is the most likely author among this pool of suspects. Another far more common problem, though, is when there is just one disputed document and only one, or a set of disputed documents, but there is only one candidate. And this problem is often called in the literature authorship verification. And now this is clearly a more fundamental problem than the other one, because you can break down any authorship attribution as a set of verification. Like, for example, here, this is one verification, one verification. Also, in terms of at least my experience as a forensic linguist, this scenario here is far more common than the other one. So most of the times in a forensic context, there is only one suspect, only one candidate, and then the question is, was this candidate the author of this disputed text? And so this is actually a very important problem. And it is also far more difficult than the other one, because the other one has a close set of candidates. And so, the likelihood that it could be one or the other can be, it's easier to determine that. But when it comes to a verification problem, then the alternative to the hypothesis that it was this author is that it could have been somebody else. So it could be a very large population. So it's a much more difficult problem. Now, there is also a kind of third problem that sometimes is referred to as authorship analysis as well. And that's when you have one text and no suspect at all. And this is a profiling problem where the task is to determine whether there is any clue in the language of this document that would point to, would narrow down the list of suspects. Now, this is not, I'm not going to cover that. So I'm only going to cover what has been called comparative authorship analysis. So there is a comparison that has to be made, or alternative, another name that has been proposed, especially by my colleague Shunichi Shiara, is forensic text comparison that aligns quite well with forensic voice comparison. But in my own, I mean, in this work, in this slide, in the slides and in this talk, you will these two are synonymous, and I will often just talk about authorship analysis to mean comparative authorship analysis. So authorship analysis is a very old field or a very old problem, not a field, more like a problem. So we can date it to 2,000 years old practice. So there is evidence and in ancient Greece, people were trying to determine who wrote something or who said something based on the language. And then, of course, in literature, there is a lot of literature on how to identify the author of certain pieces of literature. So, whether something was written by Shakespeare or Marlowe. And it is precisely on problems like that that a field of study called stylometry was developed. Stylometry meaning the quantitative analysis of style. And so, the quest of people working in stylometry was to find whether it's possible to identify a stylistic fingerprint for an author that would uniquely identify them, so that any work of literature could be attributed to them. And clearly such a thing doesn't exist. Or at least we haven't found it yet. So there isn't like a metric or something you can measure from a text that would uniquely identify an individual. And for many years, people have tried different things, and nothing has really worked consistently until a breakthrough in the 60s that was made by these two statisticians who decided to focus on function words. So if we take a text like this one, we can break it down into the so-called bag of words. So we can imagine it like a bag with all the marbles being the words, and we don't look at the order of these words. So we just look at whether these words are in the text or not. And then they decided to only focus on function words, so only on those words that don't contain meaning. And the reason why they chose to do that was because, well, because they are not influenced by meaning, but also because they, as statisticians, they were interested in using statistical methods. So if you want to use statistical methods, you have to count things, and function words tend to be very frequent in language. So the counts are more stable. And so what they did is they basically made a list of function words, and then they looked at the frequency with which authors use these function words. So you can represent the style of an author as a list of function words and their frequencies. And then by looking at the frequency of these words in the disputed text, they were able to um, classify authorship. And so this was an attribution problem in this specific case. So, but it could be generalized to a verification problem. So the idea is that you have these function words, and you just measure the frequency, and then you use that to attribute a text. And this is something that has been, I mean, since the 60s. If you look at modern methods today, it's really more, quite similar to what people do nowadays, even though it might be a little bit fancier today, so the features might be a little bit different. So we use sequences of characters. Um, Maybe you modify the frequency, so you weight it in certain ways, but at the end, it all boils down to this. And one particular method that has been successful that was developed in the early 2000s, and it's Barrow's delta, which works in a very similar way. So it still involves measuring frequency, but this time, rather than just looking at frequency, this method looks at, tries to find a norm. So, for example, how frequent this particular function word is in a corpus or in a register, and then looks at the deviation of each author from the norm. So whether, say, for example, author one overuses it or underuses it compared to the norm. And so instead of doing that, instead of using the actual frequency, it uses the deviation of this frequency from the norm. But at the end of the day, the result is the same in the sense that what is used is a so-called a vector space model, which is, what that means is that you basically have, you take each word that you're looking at, so each function word, and then let's imagine that this is a dimension on a space. And so if I have these two function words here, if I know the frequency that this author uses upon, and also then I can plot this author in this space. And it could be delta, I mean, it could be the deviation from the norm, or it could just be the frequency, right? But you can do it in the same way. And then you do it for the other author, and then you can just literally measure the distance between these two authors. And this is Barrow's delta. And then if you have a disputed text, you just do the same. And then um, sorry, yeah, yeah, just got a message about translation. Um, right. So, and then if you have a disputed text, you will just plot that in there, and then you will have the closest author to the disputed text is going to be the author of the disputed text. That's the idea. Now, nowadays, people use cosine delta, which is you measure the distance by looking at the angle between the vectors. But this is like a technical. I mean, if you're not like this is just for those of you in the audience who are interested in the technical details, but it doesn't really matter. So the point here is that you measure the distance, and then the closest one wins, and it is determined as being the author of the disputed text. And so more or less, this is what people are doing. And again, you can ask me during the Q&A. There are other methods that are not based on distances, and that's also something that some people do. But this is really a method that has passed the test of time. So we know that it works quite well, and so we kind of know we understand it mathematically, and a little bit linguistically, maybe a bit better than others. But there are still problems with it. One problem is that you're taking these function words and you're putting them in a distance. And so yes, of course, you can say this author uses upon more frequently than the other one, and then you find upon in the disputed text, and you can say, oh, right, so that's why this author is the author of the disputed text. But when you think about it linguistically, I mean, maybe it's with upon is it's a quite distinctive function word, so it might sound a reasonable argument, but you know, let's say that the function word that is used more frequently by this author is a, okay, or an, or also, or some. I mean, clearly, it's not because, I mean, the fact that that a certain author overuses or underuses these function words is not really a linguistic explanation, because it's not that authors choose these function words. I mean, clearly they don't choose them because they like them, or it doesn't represent their slides, their styles, or it doesn't represent their sociolinguistic identity. So there's no real linguistic explanation as to why function words would work in this way and would predict the author of a text, right? And then also a method of this kind is, a method of this kind only looks at really the similarity between authors. So it doesn't look at the typicality, which is another important factor in forensic science. So you should evaluate similarity also in terms of typicality. So how typical are these frequencies of these function words in the population? I mean, to a certain extent, it does that because you have a norm, or there are also other algorithms that I'm not going to explain here, but they would kind of account for typicality. But it could do this in a little bit better way, and so that's the point. And so this leads me to my argument here, which is that there is a set of desiderata that we want for a method, an ideal method for authorship analysis, and this is a method that works, a method that performs quite well when tested, but also they can be as transparent as possible. So we want to understand why this method is working. We want to be able to interpret it. And so even though we can produce this, say this list of function words that are underused or overused, it's not really an interpretation or an explanation. And then also we would like a method that adopts the likelihood ratio framework, so that it includes typicality. And finally, this is actually connected to this point, one that is scientifically plausible. So ideally, we would want to have an explanation as to why this method works. And so this leads me to my proposal here, which is that we can actually find such a method if we borrow from cognitive linguistics. And so more specifically, if we borrow from usage-based frameworks. So cognitive, or I'm going to use the term cognitive linguistics to generally mean usage-based cognitive frameworks. It's a very broad, so there isn't really a field of, sorry, there is a field of cognitive linguistics. There isn't just one framework. There are multiple frameworks that would fit into the general label of cognitive linguistics. And but most of them would subscribe to the same kind of principle. So one principle is what is outlined in this position paper, manifesto of cognitive linguistics, which is that language is a complex adaptive system that emerges from usage. And another argument that is often that most frameworks would subscribe to is that the language network that is a person's language network is a network of constructions. This is particularly the case in the framework of construction grammar, but I think other cognitive linguistic framework to a certain extent would subscribe to the notion of constructions. So, these are a few principles, again, similar to that, where that we can say that cognitive linguistics it's subscribes to. So we have that language is a network of knowledge. The memory is very important. So we have a very rich memory of usage, and we tend to rely on that. These memory traces form the constructions. Uh, Also, another principle is that words are not the unit of grammar. This is something that, for example, traditional authorship analysis, by focusing on the frequency of words or using a bag of words model of language, they tend to implicitly assume that words are the unit of grammar, words are the unit of language. But actually, we know that in terms of language processing, this is not what people actually do. I mean, we we tend to use constructions and chunks that are much larger than a single word. So the unit of choice basically is not the word. And there is no, and this is quite connected here, that there is no qualitative distinction between lexis and grammar. It's not like there is a lexicon and there is a grammar from which we get the rules of how to, combine the lexis. It's more like a continuum. And so, in other words, grammar is basically like a constructicon. So it's more like the lexicon. So it's a repository of symbols of, in this case, contractions, rather than a list of rules. So again, I'm borrowing from various authors here. So all of these are different frameworks of cognitive linguistics or functional linguistics that would all agree on these principles here. And overall, this principle, what they all say is that memory plays a very big role in language processing. So we rely on memory a lot. We tend to produce things that we have already constructed and we reuse them. And we memorize a lot from actual instances of language usage. And so from these principles, what I developed is a theory of linguistic individuality, which you can find in this monograph here, which, by the way, is free right now. So it's gold open access. You can just download the PDF. You can search now, you scan the QR code. And so in this book, I set out a theory to explain authorship analysis by starting from these cognitive linguistic principles. And the basic, the basic principle of this theory is that a linguistic unit, so the basic linguistic unit of processing for an individual, um, is something that they can produce automatically. And so, in other words, which is actually, I mean, it's not my proposal. I'm just borrowing it from cognitive grammar. So this is Langaker's definition of the basic unit of language processing. So it's something that a person stores in their memory and that they can produce automatically. And this is actually the same definition of a chunk in cognitive psychology. So a chunk it has a very precise definition, and it is basically a combination of items that is more likely to occur together. It's very similar to a collocation in corpus linguistics. So just to give you an example what a chunk is, say that you have, if I give you this sequence of letters and I ask you to memorize them all and then close your eyes and repeat them, you wouldn't be able to do that. And that's because our working memory is can only hold about 7 items. And then after that, we struggle. However, if I just take these letters and I rearrange them in this way, and then I ask you now to recollect that, you will probably be able to. And that's because you are able to chunk this in words. And then by chunking it in this way, rather than storing all of these letters, you only have to store 4 items. And so in this way, you are overriding your working memory. And so this is the principle that gives rise to chunking. And it is by using these chunks that we can bypass our working memory and produce and store more than we would otherwise. And this is it's one of the basic principles that kind of govern language processing. Any chunk is a physical change in the brain, and it tends to be stored in procedural memory. So just to demonstrate that again, so the way that chunking works is that it's basically you have, say you have 3 units that you tend to see in sequence quite often. It actually doesn't have to be in sequence, but let's say that it's the sequence. If you see that two items tend to occur together, then they just become one. And now you have two. If these two items tend to go together very often, then they become just one. And so this is the chunk. So for example, we can see that at play in phonetics. So say when you were learning how to speak English, maybe these three sounds where you were learning how to pronounce these three sounds and you were producing, or this is learning how to read. So we're talking about very early on, and you almost certainly don't remember that. You were probably, when you were reading this for the first time, you were treating that as three different items. But then as you exercise your reading, you start to combine this together and then combine this together until when you see this sequence, you just pronounce it in one go. You don't break it down into three single letters. And this is similar in syntax, right? So for example, um, it, it's possible that when you were learning academic English or practicing academic English, you were breaking down a sequence like that into these three single items. But then by seeing these items occur more often, you just learn that they go together. And especially if you produce this, you just produce it in one go. And so the idea here is that it is this chunking process that leads to the formation of these constructions. And so our language production is mostly dominated by these constructions that tend to be much larger than just a single word. And so one way that we can think about grammar within this framework is that it's something like that. So it's like a set. Oh, so the grammar of a person A is basically like a set of these constructions. And these constructions tend to be things like that. So they tend to be frames where you can have some empty slots that you can fill in based on the needs of the moment. But apart from that, they are larger than a word. Like they are also words, of course, but they tend to be larger than a word. Now, clearly, the grammar of a person changes. So we can model grammar in this way only when we are talking about a certain time t, because t plus one means that potentially your grammar has changed. But we assume that this time is actually pretty stable if you're an adult. Otherwise, for example, we wouldn't be able to do any authorship analysis. Right? So, and also we have some studies, not a lot, but we have some studies that show that it is actually quite stable over time. The other important thing to bear in mind when talking about grammar in this way is that I've been talking about chunks as something that you know you might have or you might not have, but in reality, it's more complex than that because the actual picture is that there might be some chunks or constructions that that you can produce automatically in a very fluent way. But then there might be other ones that you are less fluent with, and then other ones that you're completely not fluent with. And so this kind of how fluent you are, so how much something is a chunk to you, is what tends to be called entrenchment in cognitive linguistics. And so actually we can imagine this set as being a set, but also with a sort of level of entrenchment measure attached to it. But if we go back to, just to simplify, if we just go back to the ones that a person masters completely, then the idea is that language can be thought of also as a large repository of these chunks. And then the idea is that at every single time t, no two people are going to be identical in terms of the chunks they have. And that's because, if these chunks emerge from usage, then all people have different exposure to input. They also produce things differently, and the kind of things that they do in their life is it's different. And so because of that, they will have different chunks at their disposal. And so all of that can be explained, or I mean, it can be described as the principle of linguistic individuality. So what I just said. So any moment in time for any language, there do not exist two individuals that have exactly the same repository of chunks. Can we say that this is the linguistic fingerprint? To a certain extent, and this is not, I mean, this proposal, by the way, again, is not really mine in a way. I'm just borrowing from cognitive linguistics. So this is something that LambdaG himself said in the late 80s. So the set of units mastered by all members of a speech community might be a rather small proportion of the units constituting the linguistic ability of any given speaker. So in other words, we even though we have the illusion of sharing a lot with other people, in reality, when we look at what we produce, we are very, very idiosyncratic. And so the reason why I'm talking about this is because I think this is actually a linguistic explanation as to why function words distinguish individuals. So it's something I call the statistical approximation hypothesis. So an author key profile, which is the profile of function words that characterize you, is simply just a statistical approximation to their grammar. So just to give you an example for what I mean, say that you have the grammar of a person A, which is contains these constructions, these chunks here, and then the grammar of a person B that contains these other chunks. So these are actually alternative ways of saying the same thing, if you notice it. Now, if we imagine that we have two texts written by person A and person B, and we just count the function words. So let's say that in this text, each construction is used only once. Okay? If we count the function words in these texts, then we will see that they will have different profiles. They will have different frequencies. And that's just because the chunks in themselves, which is what the speaker actually chooses, are themselves made up of function words. And so the function words that we see in this text are simply a reflection, statistical reflection of this construction that's what they choose. So in other words, to show you graphically, this is what I mean. So it's the composition of someone's grammar that leads to this kind of differences in the frequencies of function words. And this is because function words tend to make the most of these constructions. They are the building blocks of these constructions. Okay, so now that I've laid the grounds for the theoretical grounds here, the argument is that if we now build a method for authorship analysis that is more grounded on these theoretical foundations, then the prediction is that we should also, I mean, it should be more scientifically plausible, but it should be more explorable because it would, actually verify would actually uncover what the reality is for that person. And it should also outperform the other ones that are just using a statistical approximation, right? And so we propose one of these model, which is one of these methods, new methods that, it's not necessarily the final one, but we believe that it's for now it's a good one that meets all of these criteria, this desiderata. And this is now in a preprint, so the paper has not been published yet, so you can find the preprint here, and the title will change actually. So for now, this is a provisional title, but so the method is based on the calculation of this quantity here, so the likelihood ratio of grammar models, which is what we call LambdaG. And so the method we call this method LambdaG. Okay, so if we go back to our definition of a linguistic unit, so a linguistic unit is therefore is a piece of linguistic information, okay? And because it's a piece of linguistic information, then we can actually think about it in terms of information theory. So the information theory is the branch of mathematics that that studies information. And information is basically probability. So they are connected or they are the same thing. And and so we can think about grammar as a probability distribution over these linguistic units. And so if we go back to my example of chunking, so have you noticed, I don't know if you noticed how you're basically taking something small and then you're putting it together, you are compressing it into just one thing, right? So you're basically this chunking process always often been described by cognitive psychologists as a data compression process, where you're taking units and you're compressing them into something that stands for the other ones. And so this data compression data compression is also an area of information theory. So this is quite connected because in order to compress data, you just look at the probability of co-occurrence. So all of this is pointing to the same direction here, which is that, looking at a probability distribution over units. And if you're familiar with this term, a probability distribution over units, it should probably ring a bell because that's also the definition of a language model. So a language model is a probability distribution. We can think of a language model as a probability distribution over sentences. So, for example, a language model for English would be something like that, like a huge histogram that gives you the probability for each sentence of English. And then, of course, there might be, there will be very likely sentences, but also very unlikely sentences. Another way that we can think about a language model is like a black box where we can just ask a question. No, sorry. We can we can give it a sentence or, ask a question, say, how likely is this sentence? And then the language model will return a probability. And so if you ask, what's the probability of this sentence? This is the probability. But if you ask what's the probability of this sentence, then probably it's a very small probability because it's extremely unlikely. Which, this is a probability that is basically means it's impossible. And this is it's not too different from another black box, which is our mind. So we can do the same thing too, that we can ask people, what's the probability of this sentence? How likely is this sentence? And, people will not respond with a number, but they might say it's ungrammatical or it's very unlikely. The difference between a person and a computational language model is that if you ask the famous Chomsky sentence, colorless green ideas sleep furiously, if you ask that to a person, the person might say, well, it's unlikely, but it's grammatical. Whereas a language model will still return a number which doesn't make a distinction between, how plausible it is rather than how grammatical it is. And this is also why, something like ChatGPT works very well. ChatGPT works just because by learning language, it also learn useful things about the word. And so you can ask questions about the word and it will give you these things that it learned. But ultimately, it will not be able to give you a difference between grammatical or likely or plausible. Um, Okay, so how much time do I have?
About 15 minutes, 1 5. So we have like 5 minutes left for Q&A.
Okay, yeah.
Yeah.
Okay, so the reason why I'm talking about language models is because, as I said, so they have the same definition of what I'm trying to achieve here, which is that what they are doing is that they are compressing data and they form a representation of this, a statistical representation of this data that is a compressed version of the training or what you gave it to begin with. And so what we are using but the problem with just normal language model is that they will not make a distinction between grammar and meaning, basically. So what we are using for these just conscious about time, so yeah, so let's say, so let's forget now about large language models. So what I'm talking about, by the way, this is just the definition of a language model, not necessarily a large language model like ChatGPT. So we can create a simple language model in this way by simply just counting the number of words, right? So let's say that this is our corpus, okay? So we can just count how often each word occurs in the corpus. We calculate the probability by, that's just the relative frequency. And then if we want to know the probability of a new sentence, we just multiply these probabilities. Okay? So that's a simple language model. And that's how language models used to be made before neural networks. So they were just based on counts of words. The problem with this language model based on just simple word counts is that if you just give the same words, that if you just try to get the probability of the same words in a different order, you just get the same thing. So this is still a bag of words. And so what people have been doing in the 90s was to try to use n-grams, so try to use sequences of words. So if I just now make a frequency table of n-grams, so frequency of, say, just two words, then what I can do is I can create a table like that where the word in the row is the first word of a sequence, and then I can see, okay, how often is this word followed by by dog, by on, by sat, and then I calculate the frequency. And then now I can make a better language model that will account for the position of the word. And so what we are using for this method is n-gram language models. So we're not using neural networks. We're using, so this is if you have two words. If you have three words, then you don't have a table anymore. You have like what is called in mathematics a tensor. So you have a table that is three-dimensional, because you imagine that the first word is here, and then you look at, okay, what's the second word, what's the third word, and then the cell in the middle will tell you the probability of that sequence. So we are using an n-gram language model that is of order 10. So a very big multidimensional table. But the idea is that it's still based on word counts. But in order to get to the grammar of, rather than, to avoid for these models to capture meaning, what we do is we take the text and then we mask the content words, and we actually replace them with part-of-speech tags. And so the text basically looks like that, where you have, wherever there is a noun, you have a symbol that indicates that it's a noun, and you leave the function words as they are. And so what you get, so the algorithm works in this way. So you have, let's say that you have your candidate author and you have your disputed text. You also have to have a reference population. So you have to have a reference corpus. And then what you do is you first do this masking part where you remove the content words, and then you fit an n-gram language model on that. And then what you get is the grammar model. So you have a model of the grammar of the author and a model of the grammar of the reference population. Once you have that, then using the same way I demonstrated before, you can take the disputed text, you mask the content, and then you simply ask, okay, what's the probability of this text under this grammar model, and what's the probability of this text under the reference grammar model. Because that's how language models work. They give you the probability of a sentence. And so if you divide these probabilities, you get a likelihood ratio, and that's what we call LambdaG, so the likelihood ratio of grammar models. And so what we find is that if we tested it on 12 corpora from all different kinds of registers, and what we find is that LambdaG outperforms every other method, including a large language model. So we tested it on emails, scientific papers, chat logs, forum posts, reviews, news articles, and the length of the text. So the longest texts were these ones, which were around 2,000 words, but the shortest texts were even less than 200 words on average. So we're talking about very small sizes. And in basically all of them, our method outperforms the others. Now, the other big advantage of this method, though, is that we can make heat maps using it. So if I take, once I have my disputed text, what I can do is I can take, say this is a sentence from the disputed text, I can color code each single word inside the disputed text for the value of the likelihood ratio of the grammar model, the LambdaG, because the final result of the algorithm is simply the sum of all of the tokens in this text. And so, in other words, I can pinpoint exactly what token is most responsible for the final output. So, for example, the sum of the LambdaG values for each word in this sentence is the LambdaG value for the sentence. And then for the disputed text, if I have multiple sentences, then the final value of LambdaG for this text is simply the sum of the LambdaG values for each sentence. And so because of that, the analyst can go back to the text and check exactly what part of the text is mostly responsible for the final output. And so just to give you an example, and then I'll end the talk. You can reconstruct, you can see this in the paper. So if you have, this is an example from this corpus, you can see which parts are, the heat map, which parts are the important ones. And then, so the stronger the red, the higher the LambdaG value. And then the analyst can then look up what this means. So for example, in this case, this sequence here is only used by this author, or this sequence here is only used by 4 other authors in the reference corpus. Okay, so all of this is already, so we conclude that, this method, it works, it is more interpretable, it's compatible with the likelihood ratio framework, but it also has a theoretical foundation and explanation based on cognitive linguistics. And this method here can be already used. So if you are an R user, if you program with R, then I recently developed a package for authorship analysis called idiolect, and you can install this package. And then one of the functions that you can find is LambdaG. So you can just run this already. My colleagues work using Python. So if you're a Python programmer, we will also soon release a version using Python. Yeah, and that's all. Apologies if it was a bit longer than expected, and more than happy to take questions.